Okay. Everything should be up now. The YouTube stream was giving me a bit of a headache, but it seems to be working, which is good. Not a whole lot of people watch these on YouTube anyways, but I get some comments from there, so I like to stream to both places. Right. Doesn't really seem to be anyone here yet, but hopefully people will come along as we go. Or in any case, they always have the VOD to go back to if they want to watch these. So today, Advent of Code, day number 8. We're on a desert island. It seems we'll be crossing Desert Island for a little while here. You can see the day 9 star up ahead. I guess we can just dive into it. As always, I haven't looked at this. I'm going in blind, and of course we'll be solving these in Nim, which is always good fun. Quiet day today, indeed. Right. There. I'm just getting stuff set up here. There we go. Seems to be some people coming by now. So we'll get this going. Day 8. Haunted Wasteland. That doesn't sound good. You're still riding a camel across desert island when you spot a sandstorm quickly approaching. When you turn to warn the elf, she disappears before your eyes. To be fair, she had just finished warning you about ghosts a few minutes ago. So the elf we followed into the desert was apparently a ghost. One of the camel's pouches is labeled Maps. Sure enough, it's full of documents, your puzzle input, about how to navigate the desert. At least you're pretty sure that's what they are. One of the documents contains a list of left-right instructions, and the rest of the documents seems to describe some kind of network of labeled nodes. It seems like you're meant to use the left-right instructions to navigate the network. Perhaps if you have the camel follow the same instructions, you can escape the haunted wasteland. After examining the maps for a bit, 2 nodes stick out, AAA and ZZZ. You feel like AAA is where you are now, and you have to follow the left-right instructions until you reach ZZZ. What kind of assumption is that? We're in the middle of a desert. Why would... Yeah. Anyways, this format defines each node of a network individually. For example, so RL, right, left, I guess, and then AAA is connected to BBB and CCC, BBB is connected to DDD and EEE, CCC is connected to ZZZ and GGG, so I guess that's the shortest path is to go AAA to CCC, CCC to ZZZ. Starting with AAA, you need to look up the next element based on the next left-right instruction in your input. So we're just going to traverse. We're not going to find the shortest one. We're probably just going to go by these. In this example, start with AAA and go right by choosing the right element of A, CCC. Then L means to choose the left element of CCC, which is ZZZ. By following the left-right instructions, you reach ZZZ in 2 steps. Of course, you might not find ZZZ right away. If you run out of left-right instructions, repeat the whole sequence of instructions as necessary. Right-left really means right-left, 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 and so on. For example, here is a situation that takes 6 steps to reach ZZZ. So left, left, right, and so that would be left, goes to BBB, BBB goes back to AAA, but now we have taken 2 lefts, so we're going to take a right. That brings us to BBB, and the pattern is repeating, so we go back to AAA with the first left. The second left, we go to BBB, and then we're on the right, and we go to ZZZ. Starting at AAA, follow the left-right instructions. How many steps are required to reach ZZZ? And our puzzle input, yeah, way longer, and not all of these are the same single, like one repeated letter. But we should have an AAA in there, and we should have a ZZZ in there. Right, interesting. So basically, these create a tree structure, and we have to navigate this tree structure by doing these left, right, left, right, left, right operations on that tree. So I think we'll do maybe we'll do npeg again and parse this into like a proper tree structure in memory, with reference objects that we can navigate through the whole thing. Yeah, let's do that. So for this, since we can encounter a line that references nodes that don't exist yet, which we obviously can't like have a direct reference to because that object doesn't exist yet, I'm going to show a trick that I mentioned briefly on one of the other days, but we're going to see how that works here today. So let's first create our types. We want a what did he call them? Like a location, or well, he calls them labeled nodes, but that's a bit boring. Let's call them locations. Location, and if you remember from previous days, we've been using objects. Now we're going to be using reference objects. So a reference object is just an object that will be allocated on the heap, and that we can have references, or so if you have a ref object like this, and we say we have a location of type location, this variable here is actually going to be a pointer which points to a location object on the heap. If we do object like that, then this is probably going to be allocated on the stack instead, and this is going to be the actual object on the stack. Of course, if we try to pass this object into a function, that means copying the object into that function. But nim is smart enough that so you remember that in nim we have to specify, if we have a function, we have to specify that something is a var location if we want to edit this. If it wasn't a var, we aren't allowed to do like x dot whatever, like x dot some field equals 100. We aren't allowed to do that. So nim, if location is a big enough object, the nym isn't going to copy that into the function. It's just going to pass a pointer under the hood to the stack of the caller of the function. So that's just it's an implementation detail, but it means you don't have to be afraid of regular objects. But for our case, we are going to need reference objects because we are going to have each node reference each other. So each node or each location has a name, and they have a left and a right, which is another location. But as I said, if we're parsing this with npeg, then npeg, so when we create the AAA node, we don't have anything we can set in these fields. Like, of course, we could allocate BBB up here, but when we encounter BBB down here, we need some way to retrieve this BBB. So what we're going to do, we're going to create a parse state, I guess, which is an object which has and for this we're going to need a module from, we're going to use the tables module, and we're going to say here that we have a map of locations, which is a table of string, so the name of the location, and that maps to a location. So table in nym is the same as a hash map or a dictionary, if you're familiar with those terms. Table is just another name for that. And since this location here is a ref object, that means that both left and right are gonna be references to an object, and the location in this table is also going to be a reference, a pointer to an object. So we can put the location into this table, and we can put it into one of these nodes, and it will be able to find it. We of course also need to store sort of the actual result that we're interested in. So that is, let's just call it a map that has the start, which is a location. That's going to be our AAA node. And it has directions, which is going to be a sequence of a direction. And of course a direction, let's put that up here. A direction is an enum of left, which is the string L, and right, which is the string R. And the parse state, the result of this is going to be of this map type. So now that we have our types set up, we can set up a rule here, which says just start with the map rule, and our state is this parse state object. That is what we're gonna sort of be creating. That's what we're gonna have available to us. But we're gonna see in a second, like we're going to unpack and just care about this result. So we need a map rule because that's our starting rule, and our map rule. So let's grab just the first sample input here, and we're gonna write that into a file called sample input 1, since we have 2 samples today. Kind of spoiled in a way. That looks like that. So as you can see, we have the directions to begin with, an empty line, and then a list of nodes. So we're going to say we have directions followed by a new line or 2 new lines. So the new line at the end of this first line here, and the new line that sort of creates this empty line. Then followed by one or more nodes, or node. So plus node means one or more nodes. Directions is going to match one or more R or L characters, and we're going to want to capture that. And in our capture block here, we're going to say that S, so this parse state, dot result dot directions is equals to something. So at the moment, we're just going to do empty sequence there. We're going to echo out our match here, like so. Yeah, I'm going to show off something there afterwards. And then we can just say that node for now. Actually, let's disregard node for now, and we'll do this. And let's try out our parser. So we're going to need a state object, which is the parse state. And then we are going to just echo out parser.match on the file sample input 1.txt. There we go. And put the result into the state object. And then we're just going to echo out state out result. So if we now run this, we will see that it matches okay. That's because it gets, it matches directions, it finds these two new lines. Unlike before, we haven't specified that you can't have any more characters. So it's going to match. It's going to say, yes, I matched, but I only matched 4 characters. So RL and the 2 new lines. And of course, this directions here is empty because that's what we assigned it to. But we notice that we have our RL capture here. Now, if you remember, I also said that $0 is the empty or the full match. So you can see this prints out RL just twice. So we could actually say we could not have a capture here, and just not echo out the match number 1, and just write out the whole match, since our rule is literally just this one thing, because we have our new lines up here. So we're just going to do that. And now, so yesterday we tried to run our code under the JavaScript backend, and we found that we couldn't do that because we had used a cast to string, because we wanted to run map it, and to run map it we would have to do we would need a sequence. So in secutils, actually I'm not sure you do need a sequence, come to think of it. It might have been updated. We're using map it. Item in the container. That's not very specific. Let me try something here. Echo out this $0 dot map it, where we say it dot well, we can do what we want to do, which is parse enum direction. And for this, of course, we're going to need our 2 friends, string utils and secutils, which we're using quite a bit in these Advent of Code challenges. Ooh, it seems like it was unhappy with something. Parse enum, it's a character, not a string. That is fortunately easy to fix. We can just throw that in here. We had to do the same thing yesterday because we were iterating over a sequence of characters. And of course we have to do the stringification. That actually seemed happy. Oh, cool. Right. So we now have our R and our L. Note that it says R and L here because we have specified that the string values of left and right is L and R. But if we actually echo out the type of state.result.directions, of course we have specified it up here, so it's not a big surprise to us. But we see here that it is a sequence of direction. These are not character literals. These are the enum directions. And we can say something like state.result.directions 0, that is an R, is equal to right. And if we run this, we will see that the container is empty. Oh, right. So the directions sequence here is empty. We just created a sequence which we just echo out. So we're going to grab this, remove that, and we are going to replace this empty sequence with the actual sequence that we create. So if we now run this, we will see that we have true. We have the directions sequence here. It's true. And that means that we can compare this to the enum right. These are the actual enum values, which is what we want. So yeah, now since we're doing it this way, with map it over the actual string instead of casting it to a sequence like I did yesterday, this should actually be possible to run in JavaScript. Well, I changed it to $0 so that we wouldn't have to do this part. So now I'm creating a capture. So this is going to be capture 1. Capture 0 is always the whole rule. And our whole directions rule is just right and left characters. So it can never be something that we can't parse down here. So it's going to be fine as long as we don't put anything more into our directions parser there. Now, let us create our node rule. Enable that again. So what is a node? Node is 3 characters followed by space equals space and left bracket, then followed by 3 more, comma space, 3 more, and an end bracket. So we're gonna create a rule here called label. That is going to be the rule for all these labels. So it's a label followed by space equals space left bracket, followed by a label, followed by comma equal or comma space, followed by another label and a bracket. So we're pretty strict here. We say that like we need this space here. In the previous parser, we made them a bit more general, allowed like as many space characters as you want. But here we're just gonna do the hard code, dumb and simple, sort of strict syntax. Like this would now be illegal, even though it obviously should parse fine. But yeah. So now we need a rule for labels, and we're gonna pop over to the npeg documentation, because now we're doing something that we haven't done before, and that is to say that we want to match something n times. So a pattern followed by, in brackets, the amount of times that we want to match it. And we can use the right, so we have alpha, we have upper. So upper is the set of valid characters here. So we're going to use upper. So a label is upper matched 3 times. That is a label. So now this should work, and we could now throw in the not one, so not any other character at the end of our input. Ooh, and these nodes also need a new line to end them, otherwise that would fail after the first one. So as you can see, that matched true. We have now matched our entire input, because we have explicitly said that if this rule doesn't succeed unless it hits something that isn't a character at the end, so the file is over, which is nice. Yeah, so that should work. Oh, sorry. Just a bit of a sneeze there. So now we're going to match our 3 labels here. So now we have match 1, 2, and 3 in our rule, or in our capture here. And now we can say, so here is where the logic comes in. So when we have a node, we have to make sure that we have a node somewhere. So we need to create a node, and we need to put it into this locations table. Then we're gonna look up the other 2 nodes and assign them to left or right if they exist in the table. Otherwise, we're gonna place them in the table. That means that when we encounter a node, we need to first check, has this node been created already? If so, we're just gonna update it. We're not gonna change it, or we're not gonna create a new one. So the first thing we do is we say if s.locations contains the first of our captures. So if it contains that first label, then we know that some other label has encountered this, and we just need to assign these 2. And actually, I think we're going to create these first, so we don't have code reuse. So what we could do here, we could say, so let us start with the second one. If s.locations contains the second one, that's not what we want. We want, if it doesn't, if s.location doesn't contain this, s.locations this is equal to a location whose name is the same thing. We don't set left or right here, because this is not the rule that we're parsing at the moment. And then we can do the same for 1. However, the tables module in them has a lot of these, because when you're looking something up in a hash table, it has to take this key and it has to create a hash of it, and then it's going to go looking in in a sequence indexed by the hash and see if it can find your element. And then it's going to compare the key to the initial key to make sure that this isn't a collision scenario. It's a whole thing. That's going to be, it's not slow per se, but it's slower than just having the object. So what we're doing here, we're doing it once to check if it is in the table. And then we're doing the whole thing again to set it to something, which isn't very efficient. So because of this, nym has a has key or put. Bit on the verbose side. So has key or put, it returns true if key is in the table. Otherwise, it inserts the value that we give it. I'm not sure why this doesn't say val. That should say val. So in the example here, this table contains A5 and B9, and it says has key or put A50. And if this returns true, that means the key is in the table. So in this case, it is in the table. So A is now set to 99 instead. And the same thing here, but this isn't in the table. So Z is going to be set to 50. These are a bit weird. But yeah. So what we're going to do, instead of doing this, we are going to do, and now I'm making a mistake here on purpose to show you something. So see if you can spot it. As key or put, we want to check if it has the key 2. Otherwise, put this location into the table. And did you spot the mistake I made? When we compile this, oh, we have an error. And that error is that the expression has key or put, the return value of this is of type bool and has to be used or discarded. So remember last time we talked about implicit return from functions because we didn't use that value for anything else, and it was the last statement in our procedure, it was returned automatically. Well, in this case, this isn't something that returns anything. So we have to explicitly say that, yes, I know that has key or put returns something, but I don't care. Just take that return value and just throw it away. Because what I'm interested in is the side effect of this. This is a thing which is intended to sort of APIs that have like return and error code to say explicitly, yes, I know it has an error code. I'm throwing it away. I don't care. I'm not going to do proper error checking, even though I should. Of course, you can write a procedure which returns something and they then say that it is actually discardable. And that means that it will auto discard instead of throwing that error. But that might have been a bit too much detail. I'm going a bit into the weeds here today. Not 1, but 3. So yeah, basically what we're doing here, we're grabbing this label right here and this label over here, and we're saying if locations doesn't have these two labels, just put in a location there with this name. It's fine. And now we're going to do this thing. So now we're going to use the result of this. So if it has the key of our first label, so if this has the key of our first label, we're going to do something special. Otherwise, it's going to do a left s dot locations $2, and right is going to be s dot locations $3, and we are sort of guaranteed that they exist because of this this section right here. We are guaranteed that these exist already. And if this returns something, what does that mean? It returns true if the key is in the table. So if the key is in the table, we are just going to say s.locations. Well, we can just no, we can't just overwrite it, because that would create a new ID for it, or a new reference for it. So we're going to say that left is equals to this node right here, and right is equal to this node right there. Unfortunately, there's no nice way of doing this, I think. Now we are doing the two lookups. Of course, we're also going lookup crazy on these. We could have put these two into a variable beforehand and then done this. We could have put this, because this is a reference object, remember? So we can store this in a variable, and we can use it multiple times because the reference still points to the object, and the reference is also in the table. So we could update that way. But yeah, this at least should work, if not be the most efficient thing. Isn't there some template like with xxx block in the table module specifically? Oh yeah, with value. Well, look at you, Mr. Smarty Pants. With value retrieves the value at T key. Value can be modified in the scope of the with value call. Huh. Oh, you learn something new every day. Yeah. So we could do with value that takes the table. So we can do s dot locations with the value $1. And what does it call it? It calls it value in this scope. So we can say value, and again value. So that's just a tiny bit more efficient. Ooh, but it doesn't seem to have liked it. We have a type mismatch. With value s location, capture the less, do blah blah blah. Expected one first mismatch at position. So this takes a, oh wait, this takes a value and a body. Oh, we have to specify the name of the variable. Right. And this one, this one has a body 1 and a body 2. So it's an if it existed otherwise kind of situation. All right, so we could actually do this whole thing with one. So yeah, we can replace that. We can do this with value, call it value, because that's the word I used, because I thought that was the default one. And then we can say down here that this is going to be equal to a new one. So what this does, with value of this first key, and then put the result into this value, we go through and we do this, add the left and right. So if we have this node already, meaning that one of the earlier nodes was pointing to it and it was created and put in the table. If it's in the table, then we set the left and right, because this is where we know the information we need for that. If it isn't in the table, so if this hasn't been seen yet, then we add it to the table, fully initialized. Right. That's nice. This runs fine. Directions. Start is just a ... because it doesn't have any way of representing that. Oh no, actually, because we never set start. We never actually set start. So we need to do that down here. So if $1 is equals to AAA, which is our starting point, then our s.result dot start is going to be equal to this. Of course, we could now put these, put this into each of these, but it's going to be fine. It's the parsing step. It's not going to be that slow. Right? If you now write out this start, start, that doesn't it doesn't have a way to represent that, because it's a thing that we have defined, and it doesn't have a stringification procedure. So just echo out the name of the start node. The name of the start node is obviously AAA. So now we have everything we need. Now, of course, if this was in a procedure, so if we had a procedure here called parse input, which maybe took a string to parse, we would not be returning the parse state. We would just be returning the map. So we can do this, and then we can return, or we could just use implicit return and say state of result. We could have this as an assert, or we could have this as an assert, or we should probably at least use do assert. So asserts are disabled in at least in danger mode. I'm not sure if they are turned off in release mode anymore. But do assert always happens. Of course, maybe we would want to have our own parser error thing. Actually, let's do that. Let's show off how you would do this in a proper situation. So a parse error is an object of catchable error, because we want this to be catchable. And we could, so we know that this has the match length and the match max. So this match max actually tells you something about where the error occurred. It's the furthest into the string it came without finding an error. So that would probably be useful to have in our exception. So match max, an integer. Now we can say, we want to keep this. So let's parse result be equal to this. If not, pr.ok. So if something went wrong, then we're gonna raise a new exception of the kind parse error with the message couldn't parse input. Of course, we can't raise that right away. We need to first do this, and we need to say that that this is, or we need to set this match max field to the PR dot, yeah, it was the same name, like that, and then we need to raise this error here. Of course, now it complains that we defined it and didn't use it. And of course, this should no longer use the read file. That should do X. And then we can say down here, parse input of, well, do that, oops, that. And let our map be equal to the input that we parsed out. Now it's going to complain that we're not using map for anything. We're going to say that map.start.name, just print that out, just so that it doesn't complain about that. So if we now run this, the same thing will happen. Only difference is that since we're only returning the result, that means that this this table from our parse state is going to be deallocated at this point, which means that we now sort of have wrapped it in something that actually uses a larger object, but it only returns the part we're interested in. And we've shown how in NIM you can create your own exceptions. This could of course inherit from any of the exceptions in NIM, or a defect if you didn't want it to be catchable. And we've shown off how to create an exception and set your custom fields and raise it. I really wish that someone, if you want a project in NIM, a cool little meta-programming project, could write something that would take in this, something like new exception, maybe a shorter word. And if you wrote like specific fields here, it would work with, it would, so this would be a macro. It would look at the definition of this, or it wouldn't even have to look at the definition. So just this would be a macro, which takes in a type and a name, or a message, because all exceptions in NIM have messages. And then just parse this var args of untyped for assignment things, and just set this field in the exception that we created. I would use that package all the time. So if you want some homework assignment, there you have it. Write a cool package that could use something useful. But of course, if we now had an error in our input, we would now get this exception, parse error. Couldn't parse input. Obviously not the greatest message, but that's the error. Of course, it doesn't print out anything else from this object. That is only useful if we're catching the input, or catching the exception. But we could of course do this as well, to sort of make it make the error message. What is going on? I keep doing capital W. Right. Super over-engineered for our simple thing here, but the goal was to show off some more NIM features. This stream is already getting longer than my usual runtime here. So it's time to actually do the thing. We have some YouTube comment. Leonard says, unless you inline, then you will not introduce a pointer. You were referencing creating objects, I guess. What are you teaching right now? I'm teaching, well, I'm not really teaching anything, but we are programming in Nim, and I'm just showing off cool Nim features along the way. So yeah, now we have our start. It's time to start using our input. So let's say that the current location is equal to map.start. And then for while the current location dot name is not equal to zzz, which is where we're going, have another loop over map.direction. So actually do direction in map.directions, because remember this, if we're not able to get to the end with this input, then we need to repeat the input. So that's what's going on here. This runs our input, and if at the end of this our current location name isn't zzz, then we still need to keep going. So for direction in map directions, current location is equal to case direction of left. Then we need to go to current location dot left, and if the direction is right, then we need to go to the right. And this of course just sets the current location to this new node. And then we say if current location dot name is equal to zzz, we break. That means we break out of this for loop, which will then run the check again and see that it's still zzz, and it will break out. We could, if we wanted to, because now we are repeating this check. So if we ever want to update the check, we need to actually update it in both places. We could do this as a while true, put this as a named block, say for example travel map. Then we can say down here that we want to break the travel map block instead of this. So that break statement will now not break out of this for loop. It will break out of this travel map block. So it will break out of both those loops with one break statement, and we don't have to repeat our current location. So yeah, that's nice. That was sort of like that. I think I like it better. Now, what was the actual output from this? Oh, how many steps are required to reach? Do they count? I don't think they count the first one as a step, right? So we're going to set steps to be 0. And for every time we go through the loop, we're going to increase steps. And then at the end here, just echo out steps. So I saw some debate over on the forum quite a while ago, or maybe it was in the live chats. When do you use inc to increase something? When do you use plus equals 1? A lot of people use plus equals 1 because that is what they're used to from other languages. Could of course do steps dot inc, since we have a command or uniform call syntax. But I like to use inc when I'm increasing something, when I'm iterating through something. If this is something that is always going to just be increasing, I like to use inc. I like to use plus equals 1 when there might be a plus equals 2 somewhere else. I try to keep those sort of distinct from each other and say that if I'm using plus equals 1, it's important that what I'm adding is 1. That information is important. That in this case, I'm adding 1. But in this case, I'm just increasing steps. Of course, increase has an overload, so you can do this as well. But I'm not sure if anyone uses that feature. Let's see. What do we have here now? Yeah, so that prints out 2, which is good. We're going to grab this second test input. You see how fast you solve? You do the actual solving when your input is nicely parsed. Like, I think this took me, 2 minutes or something to solve the actual thing after we had it parsed. Oops. Now run sample input 2. That is 6, which is good because it took 6 steps to go through this. So we can actually do 4 inputs in sample input 1.txt and sample input 2.txt. We could have done something like this if we wanted to do both of them, but we're not going to do that because we are actually interested in the actual real input, which we haven't downloaded yet. So let's just go ahead and do that. Pop that in the day 8 folder. Give it a nice extension. And we can run this, not in release mode or anything. This should be more than plenty fast. We did almost 22,000 going throughs here. So this is really efficient. We are parsing, of course, that will take a little while. But MPEG spits out some pretty fast parsers. It's pretty good at creating fast parsers. Of course, we optimized the logic here a little bit, and the actual solving part. This is an enum. So this case here, we're actually just comparing an integer. Is this integer 0 or 1? 0 or 1? And we're just updating one integer-sized reference field. So probably the slowest thing in this loop is this check. That is probably the slowest thing in this whole sort of critical section. This loop, our hot path loop. So if we really wanted to optimize this, we could have a field in our location which was end, and similarly to how we set this. Well, actually, we wouldn't need another field in all the locations. That wouldn't be great because we wouldn't use it for anything else. We could have an end field here, so we can say end is a location. Oh, maybe stop. End is a keyword. So yeah, stop there, and then do a similar thing here. If it's ZZZ, then we say that stop is this node, and then we can just say if current location is equal to map.stop. So now we're doing this comparison. I think that comparison, I'm not sure if that comparison only compares their references though. This might do a deep compare. Can I convert this to an int? No. Can I convert it to a pointer? No. This might actually be slower because we might be comparing the whole object. But there's certainly a way we could get around that and do that. As you saw, this program is more than fast enough. So we're going to submit this. And that's the right answer. You're 1 gold star closer to restoring snow operations. Hello. Someone said hi on YouTube. Right. So that's the right answer. Continue to part 2. I'm curious what part 2 is going to bring. Because the puzzle input hasn't changed. It's always the same input. The sandstorm is upon you. Oh, wait, sandstorm? When did the sandstorm come into play? Oh, right, when you spot a sandstorm. Line 2 of the story. The sandstorm is upon you, and you aren't any closer to escaping the wasteland. You had the camel follow the instructions, but you've barely left your starting position. It's going to take significantly more steps to escape. What if the map isn't for people? What if the map is for ghosts? Are ghosts even bound by the laws of space-time? Only one way to find out. After examining the maps a bit longer, your attention is drawn to a curious fact. The number of nodes with names ending in A is equal to the number ending in Z. So ending in A is equal to the number ending in Z. If you were a ghost, you'll probably just start at every node that ends with A and follow all of the paths at the same time until they all simultaneously end up at nodes that end with Z. For example, 111A, 111B, XXX, what? Here there are 2 starting nodes, 111A and 111B. Oh no, 111A and 222A, because they both end with A. As you follow each left-right instruction, use that instruction to simultaneously navigate away from both nodes you're currently on. Repeat this process until all of the nodes you're currently on end with Z. Until all of the nodes you're on currently ends with Z. If only some of the nodes you're on end with Z, they act like any other node and you continue as normal. In this example, you would proceed as follows. You are at 111 and 22A. You choose all of the left paths, leading you to 11B and and 22B. And so on and so forth until both of them are at this Z. So in this example, you end up entirely on nodes that end in Z after 6 steps. Right. Quantum ghosts, yeah. So that actually means that our parsing is not good today. But not to worry, we'll just do starts. It's a sequence of locations. And we're going to say if the last character of this is equal to an A. So note that I changed the string literal into a character literal because this indexing here will pick one character and there's a different type from a string. So our starts, we need to add this to that. So now we have collected all our multiple starts in here. So now instead of a current location, we're going to do current locations, and that's going to be map.starts. And in here, for direction in map directions, we're going to do for current location in current locations, items, I think. Do that. We're still counting steps, and we're counting full steps. So we're going to do that. And then we are going to do our check. And here we're going to introduce a new block called just check for current location and current location.items. If the last character in the name, if the last character in the name is not a Z, then we break out of the check. This all needs to be in the check, of course. If we go down to here, then all of the current location names end in a Z. We can remove the items from there. If we get here, we haven't broken out of this block. That means all of our locations ended in a Z. So then we can break out of the travel map block and echo out our steps. So the reason I'm using items here is mutable items. That just allows us to do this equals on current location from the loop. Otherwise, that would be an error. So there. If we now run, oh crap! I forgot to save this as part2.nym. So let's undo. I saved it as part 2, and now I'm just undoing all the changes we made, like that, and then we can open the part 2. Oops, not in nym. There. And this is our part 2 that we just wrote. Run this part 2. See what happens. It takes a bit longer, which is expected. I didn't expect it to take this long. Let us try on the sample input first, just to check that we haven't done something real silly here. Do that. Of course, this has numbers, which is a bit annoying, because that means we need to update this to be upper or a digit, but always 3 of them. Oops. Oh, and we need to say that we're looking for the sample input number 3. Let's see what happens. That prints out 6. So I don't think we have necessarily a bug. It might just be that it takes a while. So how long is the actual ending in A? So, oops, that's not what I want to do. Let's search for, let's search for 2 characters, an A and the equals. That should give us all the ones that end with an equals, or that ends with an A. 1, 2, 3, 4, 5, 6, 6. There's no more than 6 of them. have a suspicion because we are modifying this and we are doing while I'm pondering this, let's just start running the code here. So do a release build of part 2. And I'm actually just gonna time part 2 for fun. So while I'm pondering this, that can run in the background. So what I'm thinking when I'm saying that this is this thing, this might actually be updating the referenced object and not just the thing in our current locations. If that's the case, then it would mess up for the next one that comes in. Or if it encounters that node more than once, it would mess up the logic there. Or it might just be that this is quite computationally expensive and that there is a better way of doing this. So either we have a silly bug or something else is afoot. Let us, in this case, echo out maps that starts. That won't work because that is a sequence of something that we can't echo. So I'm going to do this. I'm going to write a an equer for a location, or a stringification thing for a location, and that is just going to return the name. Oh, that S shouldn't have been there. So yeah, the stringification of a location is just the name of the location. If you run this, it prints out the 6 that we found earlier with all the A's. And I want to try and print this out for each step in this loop. So this shouldn't change. That is good. Well, it's both good and bad, I guess. Yeah, and my step number for part 2 is high, very high. Yeah. So it is just the case that since all of these have to be equal to Z, it's gonna take a while to loop through all these and find the end condition. So can we optimize this in some way? We should be able to. So AAA, so it's not like in the sample input. In sample input 3, it's not like in here that since this starts with 1 1, this starts with 1 1. I guess it doesn't do that in the input either because we have this X thing. So that is not going to help us. So what can we do to speed this up? What can we do to speed this up? Going through all our directions. We're going through all our locations. And then we are casing over the direction in each of them. I mean, a small speed up would probably be to bring this check outside of the loop. I don't think that's going to be enough of a speed up, but it's going to be something. So if the direction is left, just loop through them, set them all to the left one. Right. My estimate for my slow solution for brute forcing is in the range of 700 days. My actual solve took about a second. So there's definitely a faster way of doing this than looping through all of these paths. What would that be? So we have, if I do my search again, we have these 6. Which jump to random nodes. And they all have to end up finding a node that ends in Z. So they can end on this node, or that one. That's 1, 2, 3, 4, 5, 6. Yeah. So there's 6 nodes that they can end up with. I'm guessing that they end on each. They have 1 each. Do they match in any way? Nah. Don't appear to. So we need a faster way of going through this. We need to find some piece of logic for going through this that would allow us to sort of break the game. I guess one thing we could do. So if that was part 1. If we go through for 1, so if we loop through for 1, the first one, and we find one that ends with Z, we know how many steps that took. Then we can go through the other ones, run that many steps of the calculation of going through. If they match, then it checks the next one. If that matches, it checks the next one. If one of them don't match, then we terminate early and we keep going with the first one. That wouldn't really give us any speed benefit because we would still have to go all the way for the next one. So let's say the first one we found one in 10 steps. And then I checked the next one. I looped that through 10 steps and it didn't find anything. So I kept going on the first one and it went 15 steps. The next one would then still have to go 15 steps before breaking out. So they would all still have to go from the start to the end at some point. So all of them always have to go through all of the calculations or all of the jumping. So there has to be something else going on. What happens next? If a node end, but not all, for that node. Wait, what? So if a node ends, so if it finds the sed, what happens next for that node? But not for all of them. Well, it doesn't do much. It carries on. Okay, badly phrased, sorry. I guess when it gets to that end, it gets to the end. The next one isn't at its end at that point. So both of them need to carry on. How does it carry on? It just keeps going. They act like any other node, and you continue as normal. Oh, wait. So they continue as normal, but there are only so many nodes that end with sed. I mean, it just carries on from whichever of these two was the position in the input. But does that help us? I mean, we could cache a node. We could cache like node position pairs and know the length of a path. That because let's well, not for our first example, but so let's say it goes through this and it finds one here. Then it knows that from, let's just take the first one, from AAA to ZZZ, that's the length of the input. So we're there. So we can then cache that from AAA to one of the seds is that length. And then, so right, yeah. But it's still per position because it would carry on then from there. So it would have to end up at A at this exact position for that information to be useful. And does that happen often enough? Because it's not always taking the same path through the nodes. But I guess caching, it probably repeats often enough that it's worth caching the length from the start to a Z. So if we have just a cache here, which is a cache here, which is a table going from a tuple a tuple of the label, which is a string, and the input position, which is an int. That should then map to not a location, it should map to a tuple pair of location, and length. Or yeah, let's call it length, I guess. And then current locations is not map.starts. Current locations has to be a sequence. It has to be a sequence of location. Oh, it has to be a sequence of tuples of location, and an input index. And then we need to populate that and say current locations, well, for start in map.starts, current locations, add a location, which is the start value, and input index, which is a 0. So now we have initialized. All of them are starting at 0 in the input index. And let's, for the time being, just we'll just rewrite the whole thing. So we are now going to loop through the input for steps. Wait, so let's not rewrite it. I think we can reuse this. So we're gonna loop through while true for direction and map directions. Right, so we're gonna undo my tiny optimization there, which wouldn't be enough. Just revert this back to this. Do have it like this again. Off right. Like that. So this is what we had, and increased steps. If current location dot input index is equal to steps, then it does this. Okay. I don't want you to go down any rabbit holes. I was clueless for time, and if that happens, I start looking for patterns. I found patterns, I assumed a lot, and it worked. Your approach is more methodical here. Hopefully it plays out. Yeah, I struggle with just assuming things. I'm a computer scientist. I see an input. I'm not solving for that input. I'm solving for all inputs that can look like it. So if there's a pattern in the input, I'm gonna miss it. But let's see if this works. If this doesn't work, I'm probably gonna call it quits for the day. So we have current location. So if this one is at the steps that we're currently at, then we do this thing. And we only do that. So if right, but we need to, so this input position in the cache is the input position in like the looping input. So if the current location, oh, and this should now of course be location. And input index has to increase. So current location input index increases by 1. So that should do the right thing. But if the current location input index modulated by the length of the map directions, so that is the input position. So if the cache has this key, where a label is the current location name and the input position is the input index location mod the direction of or the length of the directions. So if we've been in this position before for this node, then we say that cache, then we say that the current location, the location is, wait, let's do the with key thing again, or with the value. Do block is executed. What happens? Block is executed only if key in T, but it's not going to do anything wrong if it isn't. Okay, so cache dot with key. This, our key is this sort of complex tuple thing here. Oops. And we want the value to be just the name value. Then this is value dot location, and the current location is now a horrible name for this variable. input index plus equals the value length. So the distance we are from the beginning. From the beginning of the input. Yes. Oh wait, am I doing this in a dumb way? Well, I think it would. I just sort of mapped this visually in my head. So what we're doing is that we're caching subparts and being able to recall them. It should work, I hope. Right, so if a cache has this key, then it goes to this value, and that value is this thing, or it does this thing. So now we don't need this block check anymore. Well, we do need the block check. No, we can't use the block check anymore. We need our ends to be 0. And then we're going to have to do this a bit differently. If ends is equal to current locations dot length, yeah, then then let me actually write break out of the travel map. So in here, if this ends in a Z, then ends, then increase ends, and more importantly, added to the cache. So that means this. So cache at this horribly long key should be equal to, that's another tuple of a location and a length. Oh no, I didn't store a very important part of this puzzle. Damn it. We need our start position to be able to insert these into the cache. I think this is it's a horrible way of doing it. So we need our input position. We need basically the place we started from. So the assumption here is that there are a lot of cycles in this. A lot of parts that we can sort of reuse over and over. But we of course need to know where they started and what position they started at to figure out where they're going. So let me make a type here called a start position, which is an object that is this thing. Oops, that was not what I meant to do. Do label string and the input position. Yeah, so from start boss, then current location is not going to be only storing the location, it's also going to store the start position, like that. And in here, we need to set the start position to be a start pos of the label of start.name and input position of 0. So this is now going to add right, the location and the we don't have the length either. Oh wait, we actually don't need the length. We just need to know where in the no, we can't just know where in the pattern it ended, because we care about the total number of steps, which is the actual thing that we're looking for, is the total number of steps. Hold on, I just have to check some messages here. Right. Oh, this is missing a bracket. So the length here start position. So input pos was originally meant to be the position in the pattern, which is why it makes sense in here. But it doesn't make sense in here because we also want to know, or in here we don't care about the input, the pattern position. We care about the so what we want to insert into this cache is the what we want to insert into this cache is the node that we got to and how many steps it took to get there. So we need to know where we started from, the position in the pattern where we were, the location that brought us to, and in how many steps. Then our list of locations that we're visiting is the current location that we're at, the current position that we're at. This was a bad name. The current position that we're at. But we also need to know where we started from. And also how the start start index, again, probably a horrible name. Start index. I just want to see if this works. Start index is 0. So what I want to input here is I want to input a tuple like this into this cache. How did you notice that this was going in cycles. Like you said, you said you found a pattern. How did you find the pattern? How did you figure out that this was going on? So the location here is the location that we end up with. We can't skip to the next one. So what we're gonna do is we're gonna skip to the one that ends at the Z node. Oh yeah, we have to anyways, because we could go right or left, either. Yeah. So current location, store that as the location. The length here needs to be how long we have traveled since our start position. So the current location dot start index, and the current. Oh wow, that was current location input index minus that start index. Of course, this has gotten a level of indirection here. Getting a type mismatch in my cache. Attempting to call undeclared routine with a key. Wait, from up here. Wait, what? Oh, not with key, with value. There we go. That's also a type mismatch. What is the type mismatch? What? Undeclared field name at line 70. Current location dot location dot name. Again, another level of indirection. Now we have a type error. It seems undeclared identifier value. Well, that's kind of the point. I beg your pardon. That's the whole point with this template, is that we can pass in. I think it struggles with my key maybe being a tad complex. Maybe this will make it happy. Nope. Let me, and just to make sure that this isn't a formatting thing, let me just put this entire thing on one horribly long line. Huh. Because that's this thing that we're doing here. Cache is, oh right, because sorry, I was being dumb. This is a tuple, which is not the right type because it's now indexed by a start pos. There we go. And we need to do the same thing here, create the start pos object. Why is that a type mismatch? Type mismatch. Cache is a table. Well, that's a new one. Expected an error at this. What? What's going on there? Table of start pos and this tuple, and it's been given a start pos and a tuple with a location, and a length. It's given a tuple of a tuple. It's not happy about that. Because this is again the indirection there. Strong hint / spoiler. The pattern you noticed was every single track, start node to a Z node, was a multiple length of the RL instructions long. Right. You tried single node tracks to Z, looked at the length, reasoning from there was easy. Right. That's the kind of thing I don't like doing. We have an over-under flow on line 74. Interesting. Must have been pretty fast then, if this managed to overflow. What the fuck? Length. So adding this length causes an overflow or underflow, I guess. What are these values? These values are always the same, which makes me feel like this is that we've done something wrong here. The current location that input index plus equals the length of value. Length stored in the value field. So that is what we got from the cache. Oh, right, because it finds a location, it sets it to that location. And then it adds the length. Oh, but then this isn't equal to steps anymore. Oh, right. This should only happen if we are looking at this one. So it's only if we're at this node, then it pushes it into the future so that we're not going to look at it for a while. And then but yeah, I think that should work. The problem here is that like I could have an off by 1 error. I could have an off by 1 error. That means it would be just as slow, or like it could have an error in it and just never complete. Because my code is now just a big old mess. But if yours took about a second, I feel like this is already taking too long. But I'm curious. Output here. Just the word cache hit. Just want to see, like, do we get a lot of these in this test? Yes, we do. So I'm not entirely sure if this input index plus value length, if that is correct. If we are calculating this right, it should be though. Let's try to go for danger mode. I had a danger mode in one of the earlier days that just didn't work. It output immediately, but it output the wrong thing. I don't remember what it was, but well, I guess I have a recording of it. Let's do a release build and oops, maybe tell it what we're doing a release build of. Yeah. So this already seems to be too slow. Way too slow. You didn't want to implement the caching you do right now, so you postulated that any loop has to start and end at a multiple of the instruction length. Massive simplification, but it paid off. Yeah, I guess that is an insight that would be... It would definitely help. So it has to start and stop at a multiple of the instruction length. So in our input, so you're saying that if we had AAA, it would either at the end here find a Z or it wouldn't? So an A here could find a Z here. Maybe it does, maybe it doesn't. If it does, record that the node that started up here ended up at a Z down there. So if you're at the start of the pattern and you have a certain node, you know that you can skip a whole iteration for that one. Is that what you're saying? I'm gonna add my part 1 and my git add the sample input 1 and sample input 2 and just commit those as day 8 part 1, and then we're gonna add part 2 in its current form and say git commit day 8 part 2 partial, because it doesn't work, just so that we can revert to it if we need. Yeah, each A to Z track repeats. Yes, all different length, but each repeats. Oh, right. So it starts at an A here, and then it's either a Z here after 1 loop, or after 2 loops, or after 3 loops, or after 4 loops. Right. Let's try to implement that instead of this madness. So we have our starts. So we still need a way to track one little final step. So yeah, we still need to keep track of the solved ones. So we create a variable here for the solved parts, which is a table from just a well, now it's just a straight up name because it's always at the beginning. And then we can store how many loops it can skip. So just an integer of how many loops it can skip. Then we still need our, let's call them cursors, which is a sequence of locations. Yeah, and that is the starts. So it's a sequence of locations. Oh, actually, this needs to be a location. Skips tuple. And a cursor is just all the cursors is just the maps.starts, like so. And then we have loops is 0. We have done 0 loops, and steps equals zeros even 0. So while true, we say that loops, or we increase the amount of loops. Oh, this can't be that. This needs to be a sequence of tuple. I guess both of these syntaxes work, but I tend to prefer tuple there. Not sure why. So this is a sequence of tuples, and the this is the sequence of start locations and which loop it is at. So for start and map.starts cursor cursors dot add the start and 0. So it hasn't skipped any loops yet. So while true for cursor and cursors, if cursor dot loop is equal to loops, so if this is in the current loop, then we do something with it, and what we do, right, okay, let's do it this way. So for direction in map.directions, let me just copy this from part 1 there. Then the current location is not called that anymore. It's called cursor. Location is equal to cursor location. Cursor location. For direction, map directions, cursor location does that. At the end of all the directions, so when it is at the last one, if cursor.location.name, the last character of this is equal to a Z, meaning we have found an end. So before we start looping, we are going to store the location. But we can't store it there. We are going to store it in the cursors. Start. Also 0. If this ends with a Z, then I think I've already confused myself. Then the solved table gets a thing for cursor. My brain. Start location is location. Start is an int. Solved cursor. Start location dot name is equal to the location that we are at now, and it skips loop minus start, I guess. Cursor.loop, increase that. So we go through, we have start with all zeros, we get through here, we loop through the whole thing. Now we have gone through one loop. If we are at a Z node, then the start location, then we store this as a solved one, where the cursor is at the start location dot name, and the cursor location. Yeah, so then we store the cursor location and the loop minus the start. And solved. No, and the cursor. This of course needs to be items. The cursor. All the starts are going to be 0. If we have a solution, we need to 0 out the start. Ooh. Cursor dot start equal to loops plus 1, because this is the start of this is going to be the next loop. And of course, if the cursor dot loop is equal to this loops, here we need to implement our skipping. if solved contains cursor.location.name contains then cursor dot location is equal to let's do this with value is equal to value dot location and cursor loop plus equal value dot skips. Loop minus start. This must of course be cursor dot start, and this is the loops. We're not increasing steps anywhere, which is interesting. While true, if I get echo loops times maps dot directions dot length. Oh, map. But we're never ending. We're looping here forever. So we need our check. Oh, we don't have that anywhere at the moment. I'm not sure this is working. I think I might be going insane. For cursor and cursors, if cursor dot location dot name ends in does not end in Z, break the check. Create a check block. If we're still in the check block after all of this, then break out of the while loop. It's trying to break out of that block. Travel the map, and down here, break the travel map loop. Increase loops. We're not using steps anymore. So something like this. Is that what you did? I don't have high hopes for this. No. I don't think that was right. It should have been faster than this. If yours took about a second in Perl, much more simple. Am I still overthinking this? Your part 1 did perfectly for one track length. You have 6 starts. Yeah, so for each of those 6 starts, I solve until I find a solve. Oh, right. So I start with all my 6 lengths. Then I run all those to the end. Wait, what? Wait, so I have 6 of them. I can stop this. I have 6. I run them all to an end, which is always one sort of go through, or one or a multiple of one of go throughs. So I do that for each of them. Now I have a count for each of those starts, how many loops that took. Then I the least common multiple. Oh. Wait, what? That works? What's the input here? So this AAA, and what does an ending look like? But these endings don't go back to the start. Each repeats. So at one point. All right. Right. So they're all repeating. I see. So yeah, that's the piece I was missing. So if you look at something like this, so this, if you run it multiple times, it will at some point end up at an AAA at the beginning of a loop. God damn it. So let's just do one first. So do this. Let's do the first one. And go all the way until this name. Oh, no, not until the name ends with a Z, but until the name is equal to map.start 0. So echo steps divided by map dot directions. This, of course, need to compare with the name of that node. Not maybe. What? There. And these needs to be floats to be dividable by that. I just want to make sure that they're actually, oh, I guess they don't have to be floats then? Or do they still? Okay, they don't, good. So if I now run this, what? Just a second. Okay, so even this took too long. I'm just looking for like getting back to the start. And I don't get back to the start. I just need to make sure that this isn't changing. Nope. That's not changing. So why is this taking so long? Yeah, my part one. But no, ends on Z would not be correct because so the ending, like the Z ending here, for example, it doesn't start with any of my A starting points. So I need to get back to a starting point. Okay, this has gone on for way too long. I'm gonna call it quits there today. We didn't get a solve for day 2. Or for part 2 of day 2, unfortunately. But we do have 1 star here. We have traveled into, partially I guess, into the desert here. Not sure what's going on over there. Those are maybe the rocks that we could see in the distance. Yeah. Maybe if I can find a better solution for this, if I can come up with something off camera, I will let you know tomorrow if I do a stream tomorrow. But that's it for today. You still learned much about parsing. That is good. At least we learned something today. But yeah, that's it for me today. Have a good Advent, and maybe see you again tomorrow.